I would like to present our second speaker, Iosif Itkin, co-founder and CEO of Exactpro, who has years of experience and lots of senior technology roles under his belt. Personally, I would like to add that this is one of the rare cases of professionalism dedicated to nurturing and supporting the software testing direction in all different aspects, including education, experience sharing, and so on. Today, Iosif will talk about AI technologies used in testing, how to use AI to analyze reported defects, how to perform optimization for regression test suites, as well as examine Exactpro's model for AI testing of an exchange. Iosif, the floor is yours and can start.
Thanks a lot for the introduction, Nadia, and it's a pleasure to be here. My name is Iosif Itkin. I work in Exactpro. We are a global technology software testing firm focused on mission-critical financial market infrastructures, mostly exchanges and clearinghouses. Exactpro works with the most visible, most reliable, and demanding exchanges across the globe. Our main delivery center is in Tbilisi, Georgia, and the second largest is in Colombo. We also have offices in other countries, including Lithuania and Armenia. Of course, Nadia, thanks a lot for the invitation to us talk about our experience in testing exchanges, stock exchanges, derivatives exchanges, and using AI-based techniques in order to do it. There are many materials related to software testing on Exactpro YouTube channel. We have other fun videos, including the best a tester can get, testers, and many more. So there are many fun videos dedicated to software testing, AI, blockchain, software development, etc. Please do subscribe to Exactpro YouTube channel. You will find lots of interesting materials there. I do not have ISTQB AI certification, but I do have the one that preceded it, A4Q, Alliance for Quality AI and Software Testing. So I passed the one on the left. That was later superseded with ISTQB Certified Tester AI syllabus. You can see some differences in material distribution between two versions of the course. And the main difference is, of course, decrease in the last part, in the third part, using AI in testing. So it is smaller now in ISTQB AI, and as Claudia mentioned, there will certainly be additional work on expanding it. Today, I will like to cover the third part of ISTQB syllabus and also give some references of its applicability to testing stock exchange systems. So this is the table of contents of the third part. It was already presented by Claudia, and there are 6 different items. So I will go across them in random order and starting with AI for testing user interfaces. If you are interested in this particular topic, there are lots of materials available. In particular, do have a look at the Twitter or LinkedIn for Jason Arbon. They are working in this area with Tarek Keen and others for quite some time, and there are lots of interesting materials, blogs, videos, etc. Personally, I'm not very interested in graphical user interfaces because very soon the only interface between computer and humans will be Neuralink. So why bother on page objects, CSS properties, etc. So I'll focus more on other parts, on other protocols, not on user interface. Next, we will jump to the first one. So hands-on exercise, the use of AI in testing. As a part of discussion, students will identify testing activities and tasks that are currently impractical for implementation as AI. This could be specifying test oracle, communicating with stakeholders, suggesting improvements, challenging stakeholders, understanding user needs. So what would be the best way of reviewing this chapter, and who would be the best thing to ask about it? Of course, we can go to ChatGPT and ask him, do you think AI can do anything of the following? And we'll give the list of items from ISTQB syllabus. And then there is quite elaborate answer on each of the 5 items. And it claims that, of course, in summary, AI can be a valuable tool for some aspects of this task, but it cannot fully replace human input and expertise. Of course, it is a line. So understanding user needs, everyone probably knows about this particular story that Target AI was able to predict a pregnancy long before everyone else knew. And the key observation here is that this story is now 10 years old. So of course I can predict what users want better than anyone else. And of course, since the last 10 years, the systems have evolved. We just had limited appreciation of the system because there were no proper API to connect to these AI systems. Now, with the text-based API into ChatGPT, we can get some grasp of what is going on. So it's about hands-on experience and where AI will not be able to replace humans. The next section in syllabus is using AI to analyze reported defects. And in fact, it is a very important area for a number of reasons. First of all, when you have huge databases of defects, it is possible to apply sub-symbolic AI to explore these defects, find patterns, find duplicates, and do many other things. But there is even more specific reason why applying machine learning to defects is important. First of all, if you want to learn more about machine learning, there are many interesting materials available. The syllabus give you some structure for learning more about machine learning. There are also other fantastic materials out there available for free, including this amazing course, Making Friends with Machine Learning. And it contains a very simple description of what is machine learning. Machine learning is labeling all these things, and practical applications that are beneficial of machine learning is where we apply labels to something that matters. So if we find a task where obtaining correct labels for some data is useful and beneficial for us, these are the tasks that are ideally suited for machine learning. And in software testing, the main entity is software defect. So what is good software testing and what is software testing? Software testing is information service. Software testing is exploring software with the intent of finding bugs. And software testing is an empirical technical investigation conducted to provide stakeholders with information about the quality of the product or service under the test. So bugs, defects are at the center of software testing, and ability to correctly identify them and describe them is the main essence of software testers' job. So what is good testing? Good testing is, so what is good testing? It is, of course, rooted in some person's feelings, but how can we define what is good testing? Let's give it a try. So somebody can say that good software testing is a software testing that is 100% automated, easy to maintain, very fast, consistent, repeatable, applicable to all systems, vendor independent, transparent, at low cost. And if we will bring this list to most of the business stakeholders, they will tell us, yes, it is what good software testing looks like. In order to understand it, here's a nice part of ISTQB AI syllabus that talks about side effects and reward hacking. So everything on the left can be achieved by a human or by a software system if we just will not do any software testing at all. So if we will not do any software testing, we will hack the reward and we will satisfy all the items on the left. So it will be very fast, it will be extremely consistent and repeatable. And it is, of course, this approach, do not do any testing, is applicable to everything. So it's a nice thing to be aware when thinking about reward hacking and developing any algorithms. So the only difference between the things on the left and so what is good software testing? Good software testing is a testing that finds software defects that matter. And in order to measure software testing, we need to look at three main dimensions: testing better, testing faster, and testing cheaper. It is easy to describe what is testing faster and testing cheaper. As for better, better testing is testing that is better at detecting and describing defects. So if we have two different tools or two different approaches, and one approach is better at detecting and describing defects, then it is better from a software testing perspective. That's why when we are trying to apply machine learning to any domain, we need to find what is the most important thing that we would like to label. And in software testing, the most important thing is, of course, software defects. So if you build your data sets in a way that are helpful in identifying defects and structuring information about them, you are on the right track. If you are applying machine learning or any other approach to something, but this something is not producing better defect descriptions or better defects, then you are applying your tools to the wrong problem, not to software testing. Software testing consists of several stages. You can look into ISTQB Foundation on the fundamental test process, but essentially we need to look at the test basis and perform analysis of the test basis to look at everything that matters. And then we perform test design. We are looking at the actions that are available, and we have to select actions that we plan to perform in what order in order to explore the system under the test. Then, of course, we have execution phase where we need to execute these actions, including setup, experimentation, and observation. And then we have to interpret the output of our actions, and there are many different possibilities that can be applicable, non-exclusive possibilities. Experiment results might match our model of the system under the test, or something might be wrong with our actions, something might be wrong with the system under the test, or something might be wrong with our model of the system under the test. In fact, we can say that these activities present on the slide, they have different cognitive load. The one in the middle, test execution, is mostly mechanical. So it is solved in most of the systems where we implement CI/CD, where we have APIs for interacting with the various parts of the system, and where we have sufficient monitoring in place. So it is mechanical problem. Everything else is cognitive problem. And from our view, and probably not just our view, these problems have different levels of complexity. So the task of selecting a set of actions and filtering set of actions that we would like to perform has medium cognitive load, but the task of interpreting the result is hard. So it is not easy at all. It is possible to use AI for test case generation, and it is, of course, possible to use AI for the optimization of regression test suite. Both processes are related to each other because we know that exhaustive testing is not possible. So using software to generate scenarios, we can produce any number of test cases and test actions to perform. But in some cases, it is not feasible to run them all. In other cases, it does not make sense to run them all. So the idea of applying AI in test case generation and optimization is to produce a data set of scenarios that will be most efficient from software testing perspective. And most efficient means that they will be helpful in identifying more defects, and they will be helpful at better describing our findings. On the slide, there is a model of stock exchange testing that we use in Exactpro, and we work with many exchanges that support different asset classes, equities, derivatives, swaps, currencies, cryptocurrencies, and also based on different technologies, etc. But the main concept is identical to testing different exchange platforms. And we also strongly believe that the same approach can be applied to other types of systems. And now we are rolling out our findings from one domain, stock exchange platforms, to other domains, initially in financial sector, but we'll later look into other verticals as well. So the first step is to look into the test bases, and what we need to do, we need to digitalize the test bases. Digitalizing test bases means converting everything that we have as information about the system, the test bases, into machine readable form. So take PDF files and try to obtain a set of CSV files from them. Some protocol specifications now available in machine readable dictionaries. So in some cases, the problem is already solved for you. In other cases, the problem is not yet solved for you. So you need a way to convert whatever data is available, specifications, data, scenarios, user stories, in a form that we can process efficiently. And in Exactpro, we use two main formats, CSV and JSON, as the format for structuring our inputs. Then we take these inputs and we can produce any number of combinations. We can randomly combine actions. We can try, in some cases, apply Cartesian products. We can use more limited version with all pairs. And we also can apply pre-filtering to filter the actions that we plan to run. And then these actions stored in a relatively simple format. So my favorite one, CSV, represent input data set. Input data set can be huge. And then with this input data set, if it is huge, but in simple format, we can apply different techniques, rule-based, script-based, and also machine learning-based techniques to decrease input data sets by selecting only scenarios that will have sufficiently high weights. So the weights, how we can obtain these weights, we can discuss later. But at this stage, we already have a subset of test scenarios that we can execute. And additionally, we are developing model of expected results, simulation model that can be used both to execute testing, and it can also be used to improve the test scenarios. Because the model is something that we fully control, so we can introduce mutations, we have full information about code coverage, etc. I will cover the model a few minutes later. So we take input data sets, we execute actions, and we obtain output data set. And the same principle is applied here. We are trying to have lots of data, little code. So we are trying to store all the outputs and all observations from the system in the form of data sets that can be processed by the same simple scripts or machine learning algorithms. With the output data set, our next step is interpretation data set, where we apply property checking and we label all the things. So we apply annotations to all the messages present in output data set, and we also can link these messages to the generated test cases. And then after applying both rule-based and machine learning based checks against output dataset, we have interpretation dataset that we can later convert into the set of weights used to improve the test scenarios. And the main weights related to improving test scenarios are scenarios capable of identifying defects. So we would like to improve with every iteration the probability of producing a test scenario capable of hitting a defect. This slide summarizes types of learning that we are trying to apply in the process. We use synthetic test data generators to produce substantial data sets based on converting test bases into machine learnable form. And then we use scripts, both rule-based and machine learning-based, to annotate this data. So we can either ask software testers go and assign a number of labels related to the data, or we have scripts that assign labels, and these labels are later used for supervised learning, so to classify scenarios that were generated. Then, as we have a model and we can run arbitrarily many computer-assisted checks and apply both scripted and machine learning-based rules against them, it is possible to extract features using unsupervised learning from the output data set. So instead of having too many labels on output data set, we can have a limited subset of labels on the output data set. And then we use this information in the reinforcement learning and in the loop of regenerating test scenarios with updated weights and checking whether they are better at detecting problems or they are worse. So it is called model-based testing, but of course, model-based testing, all testing is model-based testing because all testing is based on models. But there is also a narrower definition of model-based testing is when we are trying to use more formal models that we can use to both generate scenarios and also to support the weighting or interpretation of the output. And the model that we use for exchanges follows under a category of technology called digital twin. Digital twin is where we have a physical or maybe software object, and we are trying to create a digital twin for it. The idea is that we fully control the digital twin, so we can obtain more information faster manipulating with it. And this idea is used across different industries. First of all, the best known, probably the first case of using digital twin in NASA was with Apollo 13, when simulation on the ground helped to return the crew safely after the problem. A couple of years ago, we've organized a course, Autonomous Driving and Software Testing, and there also were a number of digital twins. There was a digital twin of the road, and there was also a digital twin of autonomous vehicle. So digital twin is, most of the time you do need a digital twin if you are trying to apply AI to software testing. Because think about it this way, if you have something where you can experiment, like virtual car and virtual road, you can run experiments again and again, and produce more data. As soon as you have more data, you can use it for machine learning. On the other hand, if you put a car on the road, it is very expensive to drive there. So this is the reason why models, digital twins, are so helpful in machine learning. This is a very narrow definition of model-based testing, where we take one CSV file, then we put it through a set of Python code, and we produce another CSV file with expectations, and then we use these expectations to annotate lots of the data that we produce during our real or virtual testing. Real testing is against the real system. Virtual testing is against the digital twin, our exchange models. So all models are approximations, good to know. However, some of them are useful. And also the best version of a model of a cat is another cat. So in some cases, you can also try to use the existing system as a digital twin. And to a degree, the previous version of your software is a regression digital twin for your current version. There are important properties of the models that you should take into account when trying to use models, more formal models, to support software testing, and they are mapping feature. The model should be based on the real object, so it is digital twin. Reduction feature. Reduction feature is the feature that the model should be less complex than the real thing to be useful and efficient. And pragmatic feature. In software testing, pragmatic feature is whether we can use this model to better detect defects and better describe them. Pragmatic features here can be, several things can be considered as pragmatic feature of the models. Our ability to do code coverage, for the models, our ability to do structural analysis of the models, our ability to inject mutations into the models so we can run through more permutations required to support machine learning, and important limitations. So Claudia already mentioned that most of the models were available decades ago. The difference that happened recently is that the computational capacity, increase in computational capacity, and also increase in data volumes enabled more efficient use of sub-symbolic AI or machine learning. So if you work on the system, and we have cases where there is it is only capable of processing 1 order per second. For example, blockchain, some blockchain-based systems are like that. It means that you only have 3,600 events per hour, and the data set at the end of the day is small. So it is not possible to use this data set for efficient learning. So in that cases, we are trying to use digital twins as well. So it is not possible to get more data from the real blockchain system, but we can put many digital twins and produce more data using them. The second idea is no matter how strong is your brain or artificial intelligence brain, if there are problems in sensors, actuators, or memory, it will not be efficient. So you can have huge brain, but if you have no hands to press on a button and to press on a button sufficiently fast, you will not be able to do good or do bad or do anything. So when you're trying to link your software testing with machine learning models, make sure that the robo hands are in place. So I've mentioned that mechanical execution part is easier, but easier is subjective term. So in order to rapidly interact with the systems under test, you need to have good APIs in place. And of course, it is very difficult to learn if you are blindfolded. So sensors' ability to obtain information and store it somewhere is very important. So without sensors and actuators, there is no properly working machine learning. And the last thing is machine learning is label all the things. So you're trying to decrease volume of code, but increase volume of data. So convert everything into the data and make sure that the same algorithms can be applied to these data sets. So we are trying to structure all our data sets identically so we can run the very same thing against different concepts. So we can run extractors, feature extractors against traffic, against generated scripts, against specification, etc. So little code, similar code, different data. So this is the main thing behind machine learning. And of course, we do have more videos available on AI testing. Thank you. Thank you very much for your time.
Thank you, Iosif, for such an interesting and informative presentation.